Welcome to class. In today's video, we're going to get a little more general. So, my goal for this video is to hopefully find a format or a set of rules or something that helps us solve higher order linear homogeneous equations. We've seen so far that we know those solutions have to exist. Right? We know that there are n of them, that they are the fundamental solutions and they're linearly independent. Right? So we know a lot of characteristics about these solutions, but we haven't actually talked about how to get them yet. That's the goal for this video. So let's look at a second order problem to keep it simple at first. Here I've got ay double prime plus by prime plus c equal to 0, where a, b, and c are just constants. And you may have noticed so far in all the examples we've done, our solutions often end up looking like exponentials, or having an e to the x somewhere in the solution. So it's not such a bad idea to guess that our solution has the form e to the something, I'll call it lambda x, e to the lambda x. Now, let's just suppose we hit the nail on the head. What happens in our equation? Do you notice if we plug this expression in for y, I will get a lambda squared e to the lambda x plus b lambda e to the lambda x plus c e to the lambda x equal to 0. And this gives me a common factor of e to the lambda x that I can pull out. And what I'm left over with is something very interesting. I have a lambda squared plus b lambda plus c is equal to 0. My zero product property tells me that one of these two pieces has to be 0 then, and it's certainly not e to the lambda x. There's no power that I could give that to make it 0. But this quadratic equation in lambda certainly is. We know that lambda then is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Now, this is good for a couple of reasons, or it's consistent with our idea for a couple of reasons. Do you notice I am getting two roots out of this, and I would expect to get two. We learned when we were talking about more of the theoretical background here that we should have, for a second order equation, two fundamental solutions. But those fundamental solutions might look pretty different based on this form. You probably recall from your algebra class that I could get two positive real roots, two distinct ones, I should say. I might have two conjugate pairs, or complex conjugate pairs, I should say. And the third option is that I could just get one, except it's repeated, right? One root with multiplicity 2. And each of those three cases is going to change the way that our general solution looks. So let's take a look at them one at a time. Let's take a look at the easiest case first. If lambda 1 and lambda 2 are distinct real roots, then that means the functions y1 equal to e to the lambda 1 x and y2 equal e to the lambda 2x are two distinct functions. It's also a really good exercise to pause the video here and verify that these are linearly independent from each other. In other words, these are two linearly independent solutions to the linear homogeneous equation. We know that those are fundamental. And our general solution must be a linear combination of this fundamental set of functions. In other words, the general solution is c1 e to the lambda 1x plus c2 e to the lambda 2x. Let's go to the next case. The next case actually isn't so different logically from our first case. It's just going to require a trick you may or may not have seen before, depending on your math career. When I have two distinct complex roots, we know they're conjugate pairs, so this tells me if lambda 1 has the form a plus bi, then we already know lambda 2 has to be a minus bi, whatever they are. And I can actually use the same form for the fundamental solutions. These are two distinct numbers after all, so I would get that y1 is e to the a plus bi x, or simplifying that a bit, I'm actually going to write this as e to the ax times e to the bx I for just a moment. And similarly, y2 then would be e to the ax e to the negative bx times I. Now, depending on how comfortable you are with complex numbers, I would encourage you to try the Wronskian anyway of these guys and show that they are linearly independent. But we're going to need to use a trick both for that exercise likely and to move forward that you may or may not have seen before, depending on your math career, up to this point. Euler's formula is a beautiful result that shows e to the I theta, whatever theta happens to be, is equal to cosine theta plus I sine of theta. And this is really fascinating because it allows us to reduce our exponentials into trig functions. And while this maybe isn't theoretically necessary to do to write down the solution from here, I think you'll agree by the end this is worthwhile because we can use this trick to really simplify our fundamental set of solutions to this equation. I'm just going to look at the complex exponential pieces of each of my, maybe I should call them y1 tilde and y2 tilde, because these are sort of our guesses at first, right? Let's look at e to the I times bx. Well, Euler's formula tells me I should get cosine of bx plus I sine of bx. And when I do the same thing for e to the negative I bx, well, I'm just plugging in negative bx. But if you recall, cosine is even, which means the negative sign will just disappear. And sine is odd. Oh, should have stopped writing. Which means I can just write this as negative I sine of bx. And here's the fun part. If I add these expressions together, right? So if I add them up, I get 2 cosine of bx. But if I were to subtract them instead, I will get negative 2i sine of bx. These are also two linearly independent solutions to the homogeneous equation, which is really cool. So instead of taking these more complicated looking guys, we actually let y1 of x be, I can absorb the 2 into whatever constant I have, so I'll really just write cosine of bx. Similarly, I can absorb negative 2i into whatever constant I might multiply by, so y2 is sine of bx. And altogether, what this tells me is, in the case I have a complex conjugate pair of solutions, my general, I should say solutions to that polynomial we wrote, our general solution is e to the ax times c1 cosine of bx plus c2 sine of bx, where a and b are the real and imaginary parts of our roots, respectively. Now, the third and final case is the black sheep of the family here, when I have one repeated root with higher multiplicity. It uses a technique called reduction of order to derive more rigorously. I'm going to skip over that technique for right now. However, I will be making a video on that, so check the description of this video for a link to that one if you'd like to see how it's done. Now, when I have one repeated root, it means I have only lambda, which means I can only directly get information about one fundamental function. It is still true that I will have that e to the lambda x showing up. Now, I just mentioned the official derivation of this other fundamental solution comes from reduction of order. But I'll give you a way that you can think about it for the time being. All of our solutions, remember this whole thing was based off the fact that our homogeneous equations tend to look like exponentials. So what else behaves like exponentials in the sense that when I take their derivatives, they look the same? Well, it's anything with an exponential, really. And to keep it simple, let's just use a polynomial. We use x e to the lambda x as our other solution here. In other words, this gives me that the general solution is c1 e to the lambda x, the root that I obtain normally, plus c2 x e to the lambda x, the root I obtain normally.